throw this on you. I'll just clip it right here. Is that okay?
Traditional lands of the people of Treaty 7, who had an extraordinary history of land stewardship and care for the natural environment for many millennia. Specifically, the people of Treaty 7 comprised the Blackfoot Confederacy, which consists of the Siksika, the Kainai, and the Kainai First Nations, the Tsuut'ina First Nations, and the Stoney Nakoda First Nation, which includes the Chiniki, Bearspaw, and Goodstoney First Nations, and also that the city of Calgary is home to the Métis Nation of Alberta Region 5 and 6. I've spoken before about how this building is particularly, I think, significant from a University of Calgary point of view because it's located so close to the meeting of the bow and the elbow, which is the traditional place from which Calgary emerged, and also that as a public building from the 1960s, as a truly public building in its former life as a library, it was a place for all people to come and to get out of the cold, to use the washroom, more recently to use the internet. And I think that when this building was first opened and we had our blessing from our elder, make note of the fact that made a good spirit in here. And it's something I think as the School of Architecture, Planning and Landscape that we aim to continue to build a place where we have cities that are more equitable, recognize diverse cultures, recognize and respect the Indigenous heritage from which this land comes, and is also respectful of the environment. A large number of the faculty that are here tonight spent the afternoon with me on a very exciting tour and design workshop with the architects for our new building. I imagine that many of you in the audience that are students are going to be joining me either tomorrow afternoon or on Saturday morning for a tour. Having seen the plans and heard the architects talk about their concepts for the space, it's very exciting, and I wish we could just kind of do this and it would be ready and we'd all be sitting in a brand new space. But as we all know, as budding architects, planners and landscape architects, things like that don't just happen overnight. And so, yeah, we're looking forward to, first of all, introducing the project to you and then getting your feedback, your thoughts on the design, on the nature of our new home. What is it like to have what should a school of design look like in the 21st century? How do we learn? How do we make? How do we create spaces that are for well-being and a high quality of life while we're at the same time still doing the work that needs to be done? It's my pleasure tonight to introduce Jillian Carr, who is an alumni, is a student of mine from a long time ago, who is a partner at GEC Architecture, one of the sponsors, or a sponsor of our Design Matters lecture. And she's going to deliver some remarks and then introduce our guest speaker. Having joined GEC in 2005, Jillian's career has specialized in the programming and design of high-impact community projects across Western Canada. I've already mentioned that Jillian is a SAPL alumni, yes, back in those days, and is a registered architect in Alberta, BC, and Saskatchewan. So please join me in welcoming Jillian to the stage.
Oh, sorry.
So GEC is honored to introduce Yusuke Obuchi as tonight's guest lecturer. Yusuke is an architect, a creative, and an educator whose work and research spans the globe. He's currently an associate professor in architecture at the University of Tokyo, where he is directing the Obuchi Laboratory as well as the Advanced Design Research Lab, doing that since 2010. He holds visiting professorships at Harvard, Princeton, and the University of Hong Kong, and was co-director of the Design Research Lab at the AA, the Association in London from 2005 to 2010. And he also has a connection to Canada, having studied at the University of Toronto for 3 years, and I'm told being inspired to pursue architecture after a hitchhiking journey across the US and Canada. Much of Yusuke's work is focused on exploring the concepts of materiality, design systems, computational design techniques, and fabrication processes in contemporary architecture and design, which I'm sure we will hear some of that tonight. So please join me in welcoming Yusuke tonight for his lecture on rethinking digital fabrication.
Thank you. Okay, well, thank you, Julian, for the introduction. And also I wanted to thank Dean and also Alicia for inviting me for Calgary to give this talk. It's a little harrowing, but okay, that will wake you up. So today's talk, even though I've been specializing, researching, working a project on the digital fabrication, but wanted to give you a slightly different perspective on digital fabrication. So the title here is Rethinking Digital Fabrication. But at the same time, I wanted to talk a little bit about my cultural background as a Japanese, even though I am Japanese. I flew last night from Tokyo. But I'm not really Japanese, so whatever I say, please don't take it this is a kind of Japanese ideas and concept, but I just wanted to give you a little bit of a taste of how the Japanese cultural concept might migrate into this topic of digital fabrication. So in a nutshell, the main concerns and question I have is, what would be effective design strategy for society facing degrowth? Coming to Canada, Calgary, I think you have very different socio-economic condition than Japan. So maybe what I'm going to talk about is perhaps what you might be facing 50 years from today. So just listen. There's a voice from the future. Just to give you a little bit of background of Tokyo. So this is a picture of Tokyo around 1925. That the Tokyo back then was already about 7 million people population. It's quite large. But during the war, the city was pretty much gone, bombed out, even though the population still remains somewhat high, but all buildings were decimated during the bombing campaign by the US. So after that, there's enormous economic growth, perhaps somewhat Canada, also in Alberta too, is facing. There's lots of opportunities and ideas and constructions and how to expand the living condition in the city. So in a project like metabolism, I'm pretty sure for those study urban design, have heard of the metabolism. People like Arata Isozaki passed away a few years ago. But thinking about how the growth model, in this case, is more biological growth system, can be the strategy for architectural design as well as in urban strategies. So cities, and even though the city was pretty much gone, but still the property was kept as an individual property. So something like this is how to take up on these vacant lot, creating a core, and using a core as an access both in infrastructures and other function, and then create the entire city up in the air. This is some very utopian project. Or maybe you have seen project like this in Capsule Tower. Unfortunately, it was demolished a few years ago, but this was in 1972 by Kisho Kurokawa. Very small unit that can be aggregated, similar to a metabolism Arata Isuzaki's project, there's a core in the middle where all the access, elevators, and all that infrastructure is in the middle, and all the housing units aggregate around it. So this is some of the images from inside. Very, very compact. It doesn't even have a kitchen. There's a place to sleep, and then some entertainment. But this was a kind of vision that they had. City provides all the kitchens and all that kind of necessity, but the place where they sleep becomes more kind of a model for the urban development. So this is Tokyo right now. About greater Tokyo, it's not the core of Tokyo, but the greater Tokyo kind of surrounding. It's about 30 million people living right now. So it's a bit smaller than the population of Canada. So you can really see how dense this place is. But at the same time, we have very different social condition right now in Japan. Sorry for this is in Japanese, so some, I don't know if there's any Japanese here, or maybe some Asian can read some of these characters. But this one shows graph of the population, and then the year, that's the horizontal x-axis. So it's about 130 million population of Japan. It peaked about 2000. And you can see this, I guess there's no pointer. There's a huge drop in the population. So about 2050, this yellow highlight is showing that senior citizen, meaning that 65 and older, it would be about 40% of populations. I think Canada has very different, this is, I'm just quickly looked at in statistics in Canada, you still have this projection of populations increasing. So I think when you design buildings or planning a city, you project how city will grow and how, as an architect, can respond to these kind of conditions. However, in Japan, I just want to go back, it's no longer in that case. So what do architects do where cities are no longer growing, populations are shrinking, and the aging society that dominates, that it's a little glim picture, but at some point, like let's say 2100, I wouldn't say half, but the 40% of population is a senior citizen. So very different kind of a life, and also a kind of, the urban condition that we really have to speculate. So 50 years ago, we had this image, like what you are thinking, it's like how do you make more, how to provide these people that are increasing the populations. But what are the kind of design strategy and thinking that we have as a Japanese nation have to deal with it? It's slightly different. But as I said before, you might be facing this in about 40, 50 years from today. So how does the construction industries are facing this situation? Sorry, apology again for this characters in Japanese. But what you're looking at this is the aging populations or number of workers in the construction industry. So about 55 and older, that's about 40% of construction industries. And this is a younger generation. So less and less younger people will go into the construction industries, and more older generation, not necessarily they go into the construction industry, but stay. And without these, let's just call it senior citizen construction workers, the construction industry cannot sustain their own business. So this is what kind of facing the society right now, how to maintain the production of architecture when the workers or the laborers or the people who are involved in the constructions are very, very, let's say, seniors. I mean, very, very skillful, certainly, but very different kind of manpower than what we used to have about 50 years ago. So this is a little bit of older statistic. So with the advancement of digital technology, computation, and nowadays kind of AI, so I think the many industries are looking at slightly different way to optimize to increase productivities. So manufacturing industries in the past 20 years, in this case is more kind of 30 years, that double the productivities and efficiency. However, this red line or the orangey, this is constructions and architecture. It hasn't really capitalized on the possibility of embracing digital technology in order to expand and also to optimize their production processes. So the question is really how to deal with this digital technology, both in terms of designing and also the productions. So the quick answer is, let's use the robots to increase the productivities. So this is the house maker, it's called Sekisui House. They use pretty much all the robotics to produce all the elements and parts and then bring it to the site for assembly. Traditionally, all the parts are pretty much kind of put it together on the site, but nowadays lots of elements are already put together, like in the Kido part, and they're brought to the site, and then minimum amount of the work involved at in the construction site. So what do architects do? They very much embrace with the robotic fabrication. So student, instead they come, I don't know about here, Alicia showed me quickly a studio upstairs, but often when I started school many, many years ago, we had a pencil, we have a drafting board, pretty much sketches. But nowadays, when they come to school, they start learning from digital technology and also how that design can be outputted through those kind of robotic applications. So this is a kind of a trend that let's embrace digital fabrication, how to maximize the output and the possibilities. In Japan, it's the same, just because we don't have any people who could put the building together anymore. So we do have to rely on these kind of robotic and digital processes. But is this the only way? Is this the only way that we can optimize in order to kind of look for the future of production of buildings and architecture? So this is the kind of question that I have. So let me just shift a little bit to give you my, as I said before, my background in architecture. By the way, when I say, as I said before, Japan, I'm not really Japanese. I look Japanese, I speak Japanese, everything, but a lot of things are really Western-minded, so it's a little tweak. So let me just give you a little bit of Japanese cultural quality, and I call this as a loose fit. So I'll show you some example what that means. So this is a traditional Japanese house. Maybe some of you have seen the images. The rooms don't have any fixed functions. So in this case, there's a sliding doors that defines hallway to the room inside, depending on the light conditions. And also inside, there's the partitions. They slide in and out in order to create the rooms in different sizes. So when you put a futon, it's like a bed or mattress. When you put it become a bedroom. During the day, we put the futon away, put the table, and then becomes dining and study rooms. And when you have a proper guest, they put the little cushions on next to the table, and that becomes the guest room. So the room can be changed from one function to the other. So it's very loosely kind of accommodating different use according to who used and for what functions. Also, this is for kimono. This is a very traditional Japanese garment, the clothing. It's very unique kind of clothes because just the fabric that kind of wraps around your body. So it's only one size, or I should say two, kid size, adult size. If you grow, there's a height that you fold it to adjust the height. If you eat too much, You loosen the belt a little bit so you can have it. So the clothes can accommodate different body types and also different ages. Of course, there's a slight difference in male, female, but the clothing too has a very adaptive way of accommodating needs, in this case, the person. So what's important is what are the spacing between the fabric and the body, just like in architecture, how they actually design the space between the environment and the use. Just to give you a little contrast in the Western context, Western traditional clothes comes from a military. It has to be fit very perfectly. When you have to run, make sure there's nothing flopping around. So it's cut according to the waist, height, shoulder, length, and all of it. Just to give you a little interesting footnote, because I'm very Japanese physique, when I try to buy some Western clothes, my legs are a little short, my waist is a little short or small. So when I bought my suits the first time, the pocket on my back became one giant pocket. Because when you buy suits, you buy according to the shoulder width and comes everything as a package. So it became kind of strange. It's like, well, you know, I have to take it in, but at the same time, because my body is not really Western kind of physique, so I thought, how does these things work when, you know, when Japanese or Asian people wear such a clothes? So not to really address that, but this fashion, when you look at the fashion, so Hugo Boss and these kind of high-end Western fashion brand comes from the military tradition, whereas like an Asian from Japan, this is Issey Miyake, well-known fashion designer. It comes from the tradition of kimono or tradition. It's very much to do with one size fit all kind of sizes. And also, what I found very interesting kind of aspect in architecture and also the research is that one hand, as I said at the beginning, that there is so much investment and also possibility for exploring digital fabrication on the one hand. At the same time, there's very much on the traditional way of constructing is on the rise. So a lot of people in Japan are looking at how the traditional houses are being built. So on the left is a whole community get together to work on, this case is replacement of the roofs. It's a thatch roof. It lasts about 30, 25 years, and every year they have to clad the roof. But what's interesting about that roof is, yeah, it's straw. What happened to the leakage? It leaks, but because it's so thick, that water penetrates, but by the time it leaks into the house, it's already kind of projecting out of the eaves, so it's outside. So these kind of very loose material that can be put together with the community of the people as in the effort. This is something that people are also looking at. So what are the kind of future constructions or future way of making that is very much an advancement of technology, or something they want to go back in history, look at how things are done, may have a potential to speculate in the future productions. Another kind of thought that I just wanted to add in this talk today is a human scale and spatial order. Many buildings are designed, like this case too, this lecture hall, very much in industrial productions, little to do with human capabilities. But people are also looking at how does spaces have some resonance, some quality of humanness that becomes the element of design. So traditional buildings are all designed based on how much material the person or two or three can carry. So even though it looks very particular way, but they all have a similar weightness either a timber, stones, or all of it, has some human, not so much a dimension in the physique, but a kind of some common denominator that gives a sense of coherence, that is a sense of weight of the material. And the last kind of idea that I'm very much interested in is not to do with this AI, big data, but what about the small data that people in this images on the left is the plan of the building and what you're looking at in the picture. Minimum amount of information were given to, they didn't call it architect, the contractor, but the carpenter. They understood that plan and they construct very complex geometry of the building because the people understood how to interpret that drawing and that they can work together rather than they draw everything to the detail and construction workers or carpenter, they have to perform what's already been given to them as a contract in order to deliver the outcome. Or you can give the authority of how to interpret the drawing to produce an outcome. And in this case, it's a small data is given, but the big data comes from the carpenter's experiences and knowledge and also interpretations. And I'm very much interested in how to enhance the human capability, not so much of the power, but their ability to interpret the knowledge to produce an outcome. So this is a kind of very basic concept that I try to unfold through a means of the research through the digital fabrication. So I'll just shift the gear a little bit and show you some, not the big architectural proper building. It's a big, let's call it model or pavilion. It's big enough to call it architecture, but it's too small to call a proper architecture. But some sort of fabrication is an experiment. So this is when I was still teaching at AA. We built this pavilion together with a student and also alumni. So I'll show you quickly. Before I went back to Tokyo, I was still thinking digital fabrication is a way to go, and this is how the future construction can embrace to enhance its capability. So this pavilion is it's a 10 mil, this is a metric here, right? Yeah, 10 mil reinforced concrete panel that cut by the water jet. So it's like in a laser cutter, but with the water jet, you can cut any shape, even though it's in the concrete. So the agenda that we had at this point is like, how do you use the concrete, something that perceived to be very heavy and cold, to something light and something very warm, how to change the perception of concrete through a use of digital fabrication. So we invited alumni of the DLL, the AA, to design and also fabricate with the student. And it's quite complex. I'm not going to go into the whole detail of it, but it's very turned out to be very complex, not so much the geometry, but the structure, because none of the member is a continuous, is what they call it. It's a chain structure that's broken piece. So everything has to be synchronized through the structural capabilities. So we hire, or work together, I should say, construction engineer, structural engineer, to develop this project. But the point of this project was relatively easy model, what you see in the left, on the right. We made it in 2 days for this model. It's like, oh, so if we can make it in 2 days, how long would it take to put together this real size model? Maybe times 10, maybe 20 days maximum. It turned out to be, it took us about 3.5 months, almost 4 months. And imagine at AA, tuition is very expensive. And students are kind of, because I told them, it's like, hey, just come just after studio, just join, putting together. No, it turned out to be like an entire studio project. And I have to beg them just kind of forget about everything else, just focusing on this project. But still, it took about 3.5 months to build this thing. Why did it take so long? Because when you look at the drawing, it's easy. You just put it together like a model kit. But turned out to be what we didn't anticipate is that you can see the image on the right, that little tiny discrepancy, because we have like lots of slots that you have to put it together. If you have a 1 millimeter off in the one end, that discrepancy accumulates. So when you put it together, in the end, you become like a 10 centimeter off. And at the beginning, it will fit. But as you build up more and more, went backwards. So at the very beginning, it's relatively easy. Students are, what a big deal. We can just put it together. We can get it done in a couple of days. No, when you put it together, nothing will begin to fit at the top. So we have to take it down again. And then we put it together, and then it doesn't fit again. So you have to take it down again. So it's like we keep doing this. And at the end, we realize there is a huge difference between a precision of digital fabrication, which is a kind of military precision you can get. But the human ability to put it together are not the same, even though we think, yeah, if we can draw, if we can fabricate pieces, then we can put it together as if it was drawn on the drawing board. But turned out to be very different logic between the human assembly processes and digital fabrication. Of course, in the end, we have to put it together. So it took us a long time. We got really nice form in the end. But this is almost a wake-up call for us that there are different approaches through the making of parts to assembly if the humans are part of the whole production process. After that, I moved to University of Tokyo, where just like here in Calgary, that's a big university where I could work together with structural engineers, which we didn't have it back in AA. AA was very much an architectural school, focused only solely on the design, a little bit of fabrication. But here at the university, I thought structural engineer, material engineer, all of those people can be part of the team to put a building together. So I continue to develop the work through the kind of scale pavilion as a form of experimentation. So this project is a tensegity structure. Even though it looks relatively normal, but because of tensegity, this is the big, everything is hanging. So you can see all these elements are suspended from here down to in the middle. I'll show you in the drawing to show you a little bit more. But the idea is how to use the structure as a way to counterbalance human inaccuracy through the structural systems. So, as I said, this is all the elements are suspended from. And then in the middle is almost a counterweight. So because this is pulling down, even though there's an inaccuracy in the system, everything gets a little bit tight in order for the structure to be always in the tension. So human will put it together, or human, in this case a student, will put it together a little bit loose, but the design of structure is always balancing in order to make the structure stable. So the whole structure is suspended from here, going down, and this is the heaviest point in pulling down. So a little bit of discrepancy in the production that can be compensated through a design. So that we thought this could be the kind of one way to approach with the precision and the imprecision at the same time. And we kind of move on to say, hey, let's really try to explore this idea of tolerance or inaccuracy of a potential design element. But up to that, we are still very much on the production as on the one hand, and production, I should say, designing on the one hand, and then assembly on the separate kind of game. But we thought, how do we start embracing the production processes or assembly as a means of design, rather than here's a designer, here's the people who assemble. How do you marry or cross those two different aspects of making? So we use 1 million chopsticks in order to produce this pavilion. Why chopsticks? I'll get to the moment, but we very much, I think here too, I saw upstairs with Alicia's studio that, minimum surfaces, how to optimize the least amount of material in order to produce the maximum output. And a lot of concept came during the last environmental crisis in the 60s and 70s, where people begin to understand the materials are finite, not the infinite material. How to embrace that idea of those minimum material to do things in the most effective way. I'm showing you a picture of Mount Fuji because Mount Fuji is the symbol of Japanese culture, but most of the mountains are ranged between angle of 35 to 36 and a half or so. Because when you drop the gravel or sand or aggregate, most of them will stabilize itself at this angle of about 35 degrees. So we say, hey, maybe this is some sort of optimization process in order to maximize material, but at the same time, we can embrace the structural capability at the same time. In Japan, I'm sure they hear the same way, that recycling is a pretty big deal. And they even recycle chopsticks too when they have an event. So we thought, hey, let's really embrace with sustainability agenda. When we have an event in the campus, there are a whole bunch of chopsticks available. It turned out to be quite disgusting, so we didn't use that. But as an inspiration came from, it's like, hey, because when you do a project, the material gets really expensive. If you have 1 million, like if you have 1 cent chopstick, if you have 1 million, it's just quite a bit of money. So how to, do things in a way that doesn't cost the project, because our lab, maybe, I don't know here, very, very tight budget. So we always wanted to maximize. But unlike in the gravel, when you drop chopstick, we found out that it won't become 35 degrees. It actually binds them together like this. Like you can grow vertically. And if you can change a little bit, you can even generate curvature. And I say, hey, that's kind of interesting. Why do we explore this idea of dropping chopsticks in order to produce those kind of wall conditions? So we start to develop chopstick dispenser. But this is, in fact, what we are thinking is how to produce a human-driven digital 3D printer. That you will go to the places where you drop chopsticks, and you can print it instead of printing with your plastic aggregate. In this case, we print it with chopsticks. But because the height limitation that we can have, so we mix it with glue. So this is a very crude version of what we imagine as chopstick 3D printer. So this one guy, he's holding device, chopsticks dispenser. The other one, we have this crank that we crank it, this drop chopstick. And then third guy is applying glue as it goes down. This is a kind of very kind of crude version of prototype. As I said, our lab is very, I wouldn't say poor, but we don't really have luxury of you guys have robots buy every year, that kind of thing. So instead of we buy robotic arm, we just use student arm. as an exploration of studio. So what goes end of the arm is our investigation. So in this case, this whole series of chopstick dispenser that we explore. So this is, as I said, very early version of it. Here's a crank, here's a roller, and then chopsticks is it's like a cartilage. And then when you crank, the chopsticks goes. So I just want to give you a quick, kind of development or evolution, if you like. From the hand, we got the motorized, got the little improvement, the different type of feeding system. Instead of sandpaper, we got this, little bit more sticky kind of thing. And then we also start to control the amount of glue with the suction that we apply. So these are kind of series of exploration that we go in order to develop this chopsticks dispenser. In the end, it's looking kind of fancy. So this device has a microprocessor. It understands the locations, where that is. We couldn't quite manage the time, but our initial idea is when you get to the right place, the switch turns on, and then chopsticks is kind of dropping, with also the glue that attached to it at the same time, trying to kind of make everything automated. So humans are kind of carrying around these things dropping at the same time. It didn't quite work that way, but at least this is how we imagined at the very beginning. Turned out to be very heavy, these things, and especially when my students are kind of got a little tired. So okay, it's a little archaic image, but this is the kind of image that we're dropping chopsticks. So how does these things work? How do you print pavilion with these chopsticks? So we have here the system of the projector and 3D scanner. The projector will project the image. That red means don't aim at it. Green means aim at it. Purple or blue means you made a mistake. But how do you articulate to differentiate mistake from a correct one? Because it's such a rough scale. If you take the part from the blue out, the blue part becomes green, but then green becomes a blue again. So there's no mistake in this place, in this whole process. It's really kind of guiding how to operate this machine. So this is this mock-up that we're building. In Japan, we also have to wear a helmet, even though we're inside of that. We're developing how this whole system might work. While we're printing, just like the 3D printer, we print it by layer. 3D scanner constantly scans it to see if we are printing properly. Because it's such a rough, and as I said, mistake is part of the process. So we wanted to correct that. So 3D scanner scans what it's been built, run through the structural analysis, and see if this is the rate of scanning or the layering or building, will that collapse? And then if it's going to the wrong trajectory, that 3D structural analysis is updated to guide where the next layer should be printed. It's a kind of real-time both structural analysis and actuating how to print at the same time. So it's kind of interesting. The outcome is always different each time when you print it. So as you go to the top, because of the conditions that allows them to kind of modify. So this one, we aim for relatively straightforward tube, but because when you go up and high, it's difficult to operate, so it became a little bit irregular shape. But this is optimized because the structural analysis is always running. So what you get in the end, structurally optimized, but it's differentiated from the very beginning. So what this means is that people who are building are part of the design process, and the mistake that they make are not the mistake, but rewarded as a design element at the same time. So they built the kind of a personal relationship with an outcome. Because from our point, is what we wanted it, it's not how things will look like. We wanted to make sure that things will stand up properly. So who does it? Who is part of the process? In what context and what condition always differentiates itself. Just like the way that when you plant trees, depending on the sunlight, depending on how much you take care of it, depending on the environment, it always grows slightly different. So maybe the architecture is the same way. How much you involve in the construction process, outcome is always differentiated. So we built using 1 million chopsticks in front of our school. And the camp, we have to get a permission from the university. And the only requirement that they gave is it have to be functional. It has to be some public use. So we built this very spiky bench that not very comfortable, but they have to, not have to, but they use it in order to enjoy this chopsticks pavilion. So this is a kind of very early project that we thought how to embrace the human capability. In this case, is the vision, what we see, how accurately it can produce output that is always optimized. We used 1 million chopsticks. We got pretty much what we wanted it, but the outcome is slightly different from what we anticipated. But instead of calling this is wrong or mistake, maybe this is actually good because outcome is an effort, collaborative effort of everyone's participation, and everyone who involved in construction is a part of the design processes at the same time. So we wanted to kind of extend that exploration as a human capability that becomes the embodiment of the architectural output in the end. So we thought, how do we also, not this case is a vision, maybe their physical capability, or physique. And we studied with, everybody has somewhat similar kind of bodily, in this case, a swinging arm. Like if you tell them, people, just very simple instruction, bend down, touch the ground or floor, and then bring your arm up as if you're drawing arc. And very simple instructions, but we thought, can we use these kind of physical movement as a catalyst for constructing pavilions? I know it's a kind of random thought, but it's like, hey, why don't we just use the physical differentiation as a means to generate kind of basic design principles? So these are kind of a catalog of who is doing what movement and what arc that they draw. So how do you turn that drawing arc, all different, into actual building material? So we thought, why don't we just spray form as if you're drawing the arc up in the air? It's like a 3D pen, like a 3D drawing pen. So this very first is very gooey stuff just comes out. But as you can see, in the end, we managed to make a pretty good stick, if you like. So when you spray, this mesh comes out, and this mesh becomes a casement for the form, and then also become a structural reinforcement. So students will draw the arc as their kind of ways to create the expression of their physical movement. So it's very similar to the previous exercise, that there is the idea of geometry they also wanted to produce, but outcome is always slightly different. So we create almost like a choreograph of who does what. So we line up the student. You're good at this shape. You come to draw this arc. She comes to this and draw this arc. But dotted red means what we wanted it, and the purple is what we actually built. And then we scan it, and then next geometry is redrawn or redesigned based on the previous analysis. And also we learned from the previous chopstick project, which was in Japan, not sure in Canada, above 2 meter construction, you have to have a license, which we didn't know. So we thought, gosh, we don't want to go through the whole, some sort of workshop or some in order to get certified. So we designed and built everything on the floor. We lift it up and we drew arc. And then we lift it because it's form, it's very light to lift it. So the bottom ground up instead of constantly laying on top of each other. So, process goes like this. So on the left is what we imagined at the very beginning. On the right, this is a scan image that we printed it, is what we have in the end. So it's pretty close, what we have. Just this huge gash, which was when a student lifted it, there's some mistake or something because we have to plop it up. So they rotate it for some reason. So calculation gave a different kind of analysis. But in the end, this is the analysis. The red means it's a weak in the structure. Blue means it's okay. So there's a little bit of weakness on what we built it, but it's pretty compatible in terms of what we imagine, what we built. So again, the structure is a kind of way to validate the outcome, not so much how things will look like in the end. So this is a kind of physical capability that everybody has a different, and your input, not as a mistake, but the differences in how you do things became the embodiment of the final outcome. The next project, I just want to show you a couple projects of how we kind of explore the idea. So we tried, I'm skipping some other project, but different human capability became embodiment of the output. So we did a vision, we did the physical kind of dimensional differences, and we also did some strengths and others, but this is to do with the sound. Everybody has a different capability of hearing. Instead of, here's a master drawing or master plan, forget about who you are, build what is designed, versus everybody's different. How to use the differences in the individual as a catalyst and embodiment of the final output. In this case, is an acoustic. So how do we know everybody hears different? We didn't know. So we said, okay, let's try it out. So the student blindfolded, and then we gave some sound from a different location to see, can you hear or can you identify the source of a sound? And so this is a very crude experiment, if you can call it experiment, to see everybody has a different acoustic environment or perceptions. It turned out to be very all over the place. And this is a kind of diagram of how far that is. But we thought maybe this is too crude to call it even pseudoscience. So let's be more scientific-like. So we developed this 3D acoustic perceptual testing device that student has this iPhone head, and then when they hear the sound, this is a kind of mapping of it, they aim at this iPhone to see where the sound comes from. So this is a kind of, on the left, on the right, on the bottom, it tells you that if you hear the sound, try to aim it. So we try to link it together, the digital kind of, in this case, is a sensory system to the human perceptions. Turn out to be also, with this system, it's all over. And realize that people hear very different. So we all, like today too, we all think that we are in the same room, but we are in fact living in a different acoustic environment depending on your capability. And turn out that for those who use or who plays game all the time, they're very good at it. Whereas like myself, I don't play. I can't tell where the sound comes from, which is kind of embarrassing, but it's interesting. Like you can see on the top, or upper part is very difficult to identify, but like this Sophie, she couldn't tell. The red means you don't know where the sound comes from. Whereas Sheer, like she has no clue like myself where the sound comes from. But some are very good at, like Mika, plays game all the time, very good at the sound source. So how do you make architecture, if you can call it architecture? Fabrication process based on this. So we developed this shooting machine based on where the sound comes from. It's like shooting birds. So, but you don't want to shoot heavy material, so we shot coconut fiber. This is just the university said, make sure that you don't hurt anybody when you build this in the campus. So we shot the coconut fiber. Again, it's not 1 million, but it's a 1 ton coconut fiber we imported from Thailand. Made the coconut ball, and we shot coconut fiber according to the sound that you hear. And can you make architecture purely by acoustic perceptions? Again, everybody hears a very different thing, but the differences are the key to the design rather than being penalized because you are different from everybody else. So this is a kind of rough sketch of what we wanted to build. So again, very heavy, even the coconut. It's 1 ton coconut fiber in the top, but supported by this very skinny, ranging from 7 millimeter to 15 millimeter steel rod that up to 5.5 meters. That if you place all the coconut evenly, this will stand very stationary. But if it's a little bit off, it'll collapse. So we have to aim properly in order to position these coconut on the right place. And turn out that we cannot really shoot that far. So we place the shooting device from out to in order to shot into these Voronoi basket. And as you can imagine how rough this thing is, you shoot, but when a windy day, it landed in a different place. So again, similar to the previous exercises that we did, there is the people who scan in the evening what are the angle of the steel rod in order to compensate, making sure the structure won't collapse. But turned out to be, because we first made all the sample, everybody participate, did many, say, trial to see what's your acoustic perceptions, meaning that system want you to shoot this, but this person actually hear the sound comes from this. So the computer understand the person's acoustic perception and compensate. So if you want to shoot this, the computer tells to shoot there, so this person will shoot there, that kind of things. So they're kind of constantly negotiating with the person's abilities. Computers understand your personal acoustic perceptions, but turn out that people became good at why they're shooting this thing. We don't want them to advance. We then want to stay the way they register. So the computer, we have to run through the algorithm in order to de-learn the person's ability to improve in order to shoot in the right place. So it became a kind of very complicated computational processes where we understand the person here in a certain way and then compensate that in order to shoot in the right locations. So as I said, there is a night people, they go out in the evening to measure the angle of the steel rod, how much is off. And then depending on the angle of the steel rod, they recalculate it for the next day's shooting. Because this was about 14 days shooting every day in order to create that roof of the coconut. So this is the very end. Luckily, we got everything, all the 1 ton coconut to be positioned. But this is a kind of exercise how the human ability, in this case, the acoustic perception, intertwined with the computational processes of understanding your hearing capability, but also aiming capability at the same time. I just want to show you this very last project, which was supposed to be constructed in 2000, I think it was 22, but in the end it was 23 because of the COVID. This is the Venice Biennale for UAE Pavilion, that we were not main architect, but we were as a consultant in order to come up with a system and they pretty much design the final output. We call it, they call it wetland. So many of the projects I show you, what they call is additive manufacturing process, where individual element, be the coconut fiber ball, or the sticks or chopsticks, those are accumulated in order to produce an outcome. There's an enormous amount of the research and also academic context that really trying to harness that in order to produce the construction system. And then one of the research, kind of leading figure is the ETH Zurich, that they do quite a bit of the robotic fabrication in order to produce the outcome. But most of them are quite calculatable material. In this case, is brick, and the machine tells where the robot goes and where to place it. No, it's very complicated process, but possibility of automation in the digital fabrication on-site processes isn't a very difficult task. But we thought maybe embracing 100% on the digital processes, once again, how the human can be part of the process in this. So we developed the unit, unlike in the brick, which is a homogeneous material, they're all the same. We design very irregular shape, like we call it coral reef, that can be aggregated to produce the final outcome. And in this case, what is important is not so much about the placement, but friction, which is something very difficult to analyze computationally. But humans are very good at it's the right frictions or less frictions. So we thought that's something that we can try to embrace what computers are good at, which is calculations, structural analysis, so forth. But humans are good at very intuitive understanding. Is this stable? Does this have enough frictions? So something humans are good at. Why don't we embrace that and let the difficult aspect, which is calculation, so forth, let the computer handle these things. So you can see this very simple unit can be aggregated to produce the final outcome. And this is during the COVID. We couldn't go to Venice. Initially, we thought all the students would go like army of people, make these units, and then put it together. It turned out that none of us can go there. We can give only instructions how to do it. So we thought, and also, once again, very limited time, meaning that we have very little budget. So we said, hey, let's just ask them to make a groove on the ground, pour concrete to make irregular shape. It turned out that Italian people didn't want some irregular shape, but initial idea was you make that very rough aggregate in order to produce, in this case, about 2,000 pieces. So this is a very early stages of experiment, how to make in the unit. And the individual pieces are, sorry, did I get it? Yeah. Are placed in order to create this structure. But the placement is always the kind of, if you're just getting right balance and frictions. So how system work is you pick up this unit and place to roughly the area, and there's a light that we developed, the sensor turns on. And when the light turns on, you're in the right place. Find stable position within that area. And then this is a very simple set of instructions. And then once it's placed, and then you register with the scanner to see the center of the mass of the individual units are position, the registered. Oops. I'm going backwards, sorry. So as I said, if you're in the right location, the light goes on. And then you know that you're in the right zone. And then once it's placed, and you go back and then register the locations. So this is a very simple process. Instead of this is the right geometry of brick to be placed in the kind of accurate locations, we give them rough guidance. You're in the right area, but find out the most stable, most snug friction area to stabilize the construction. And each dot becomes these markers that later on becomes the key for a structural analysis. So we build in both the digital kind of twin model. So this is the kind of real time, we're building the real things, and also the digital model at the same time. So we develop this kind of chain link between the different structural analysis, the scanning processes, and and also the linking through the modeling analysis. So those are kind of quick, kind of rough scanning, and that in the end allows to create a digital and a physical at the same time. And we also have to try it out, making sure those are structurally stable. And all the project, including a chopstick, that we run through the structural analysis in order to define the Yang module, and we run into the ANSYS model that our structural engineer, Professor Jun Sato, developed his own software. And then turn that into the structural analysis model, and then determine whether the geometry we're building is stable enough or not. At the bottom, it's very thick. It's almost like a meter wide, but as you go up, getting thinner. So you make one layer, just like chopsticks model, and then you scan it, and then you go to the next layer, and you scan it, and so forth. But the human, or in this case, Italian laborers, are only given a guidance of the light comes on, and then find a place, rather than they have to read the drawing in order to build according to what is planned. And we are anticipating these kind of, let's say, a structural guidance model is loose enough that anybody who are not part of the construction industry, they could participate in the building construction processes. So I just want to go back to how I started the talking today, that in Japan, less and less people are available for the construction. How anybody, like part-time high school student, if they wanted to have construction job in the summertime, how could they participate without going through the years and years of training in order to be the part of the manufacturing construction processes? Or the guidance processes like this help the unskilled workers and labor in order to join the construction force. So this, in the outcome, the Venice Biennale organizers are very worried that it's going to move and collapse. So we have to monitor throughout the entire exhibition, make sure that pieces are not moving. So this shows that things are very stable throughout the entire exhibition period. I think this is the last one. So, so in the end, it's pretty amazing that we got a golden lion for this exhibition. But I think people are very intrigued by when I think many digital fabrication research focus on what you can build and what form, what performances, and how much of the optimization you can make, but not focusing on who makes it, in what context that laborers or manufacturing kind of processes is part of the socio-economic kind of issues that many countries, particularly in Japan, are facing. So I just want to conclude my talk with quotes from Buckminster Fuller that there is no such a thing as a failed experiment, only experiments with unexpected outcome. Thank you.